So definition of bijection. A function f is a bijection bijection from A to B if f is 1-to-1 and onto. So a function is a bijection if and only if it's 1-to-1 and onto. Why does that matter? Well, it matters because if you think about it, if you have like A here and B here, 1, 2, 3, A, B, C, whatever it is, if the function is 1-to-1, that means that no two things in A go to the same thing in B. So we can't have that or anything like that. They're all going to go to their separate things. And if a function is onto, that means everything is hit. But here's the thing to think about. I wish we had like a whole class for this. If we can draw a line between everything at A to everything in B, right? We can draw a line like this, where everything in B is hit, and no two things in A go to the same element. What's that mean about the size of these two sets? It means they're the same. I mean, think about it, right? Like, I have 1, 2, 3 markers here. And I have 1, 2, 3 pins here. How do I know I have the same number of markers as pins? I know because I can match them up. I can relate them like this. I can pair them off and go, okay, there must be the same number because each marker relates to a pin. There's no pins left over. That's exactly what's happening here. In a certain sense, what 3 means, the definition of 3 is just the term we give to the size of all things that we can pair up to these markers right here. If you compare them up to these markers right here, we call it having a quantity of 3. It's weird to think about. The point is, if two sets, if there is bijection between two sets, their cardinality, which is a fancy word for their size, must be the same. So, last definition. Sets A and B are said to have the same cardinality if there is a bijection from A to B. Because if there's a bijection from A to B, that means we can pair up the elements in A and B. If you can pair up the elements in A and B, well, of course, they must have the exact same size. That's the idea. And so I will say note, one example, and then we'll leave. Example z and 2z, which remember are just the evens, elements of the form 2n such that n is in z, have the same cardinality by f from z to 2z such that f of n equals 2n. We can show that this is a bijection, and we can show this is a bijection from z to 2z, meaning we can actually pair up the elements of z and the elements of 2z. We can pair up every integer with every even number. And so in a certain sense, there are the same amount of even numbers as there are integers. It feels weird. It feels like there should be less, right? Because like every other integer is odd, right? So there should be less even numbers than integers. But in another sense, not really, because if you look at a number line, we have 0, 1, 2, 3, 4, -1, -2, -3, -4. If you look at the evens, so the integers are all the blues, and the evens are all the reds. And if you think about it, because these go on infinitely in both directions, if you stretch out the number line, stretch out the blues by double, you'll hit the reds. So it's not that there's less even numbers than integers. The evens are just more spread out. They have a lower density, but because we have an infinite number line here, that's okay. And we do this for a lot of things. And so I'll say common notes, common facts, z and n have the same cardinality. Z and Q have the same cardinality. And then we have 0, 1 and R have the same cardinality. And we have that R and N have different cardinalities. And anything in here anything with finite cardinality. So if you're just like the set 1, 2, 3, you're just like your 3. Anything with finite cardinality or cardinality same as n is called countable. Anything with cardinality greater is called uncountable. And then we're done. These are a bunch of facts that I need to spew out at you. It would be insulting if you guys didn't see these in the discrete math class. We went a little slow this year, so we had to kind of pack in towards the end. So sorry about that, people. But anyway, the class is over. The class is done. We're done. So yeah, does anybody have any questions? All of this stuff we covered at the end, we're gonna just briefly touch. in the exam, more in a factual way, not in a way you're gonna have to actually like do anything too extreme because we didn't get a chance to do much with it, sadly. But yeah, any questions?